Hello everyone. So this is the very first Advanced Higher Maths video that I'm going to have done here. We're starting off with the differentiation unit. Um, let's take a wee look at the learning outcomes for that. So it is quite a sizable unit. Right? There's a lot of different parts to it. Um, I won't read through them all. I'll publish them in the notes. But this week we're going to be focusing really on the first two, differentiation from first principles and understanding and applying the chain rule. This video lesson is going to cover the first one here, where we're going to have a wee look at differentiation from first principles. So let's get started. Now, just to start off with, I thought about doing this as a video on its own, and I decided against it. But really, what we're looking at here is just that very first exercise zero, revision of the differentiation work from higher. Um, so I thought I'll do a couple of minutes just running through this, just in case you needed any reminding. Really, the first 5 bullet points here are very straightforward enough. The first one is just the basic definition of differentiation, multiply by the power reduced power by 1. Number 2, number 3 are the derivatives of sine and cosine. Remember, it's very important that the angle you use must be defined in radians. For number four is a bit of a funny one. You don't often see number 4 written, but I figure it is one that's written in a lot of maths textbooks. And at this level, you probably should just see it. So if a function is kg of x, right, then the derivative is k times g dashed of x. And that can be a funny one to get your head around, but basically it's saying if f of x was something like 4x squared, right, then you could take the kind of g part of it just to be the x squared. So the derivative would be 2 times 4, yeah? So the derivative would be 8x reduced to the power by 1. So that's really all that's saying, is that you would just multiply k by the derivative of the x squared. The derivative of x squared is 2x. 2x times 4 is 8x. Number 5 is just about sums. If you've got a sum of terms, sum of functions, then the derivative of that is just the derivative of all the terms. The last one, which is the one I want you to spend a bit of time on because it's the first technique we'll use at Advanced Higher, is the chain rule. So broadly speaking, you had two sorts of processes. If it was a bracket, if f of x was something like 2x minus 1 to the power of 3, you could differentiate it by differentiating the bracket. 3 times 2x take away 1, reducing the power by 1, and then multiplying by the derivative of the bracket. So the derivative of 2x take away 1 is 2. So that was one way of using the chain rule at higher. The other way was for trig functions. Let me finish writing this out. 2x take away 1 squared. Now, the other way was if it was, say, a trig function. So say it was 3 sine 5x minus 3, something like that. Then again, f dashed of x worked slightly differently, but you would just differentiate the sine or cosine part. So we would have 3 cos 5x minus 3 starts off, cosine being the derivative of sine, and then times the derivative of the bracket again, so times by 5, and a final answer of 15 cos 5x take away 3. So that was just to just to squeeze in a wee example there as general. It's quite important that, as I say, it is going to be one of the first things that we do look at in the advanced higher course. You should also know, right? So these bottom 5 things: Newton's notation, f of x and f dashed of x; the Leibniz notation, y and dy by dx, and how to use them. It's quite important at this level that you are consistent with them. And the final 3 are just common skills involving calculus. find the equation of a tangent, find the stationary points in nature, and hence draw curves, and then everybody's favourite, solving the optimization problems. Alright, so that's just a little overview of the differentiation skills from higher. Hopefully you're getting on or have gotten on okay with exercise 0. If you're stuck, let me know. Right, let's have a wee look at differentiation from first principles. Now I'm going to start with a little bit of a disclaimer. This is not something that will be in the exam. It's not something they examine or assess. They don't say you're never going to be asked to differentiate from first principles in the exam. But it is a widely accepted understanding that anybody studying maths at this level should get to grips with the ideas behind differentiation from first principles and at least kind of give it a go. If any of you go on and do any sort of maths or engineering at university, you will be working with this, I suppose, this type of maths, and at some stage you can't really get away from it. So you might as well have seen it. So as I say, I'm putting that wee disclaimer in there to start with because if you can't manage to actually carry out differentiation from first principles, so long as you understand the concepts behind it, then you're going to be okay. So starting off with this graph, this is a graph that you should have seen it higher, and it is basically the introduction to how differentiation came about and how it measures the rate of change around the curve. So I've got my blue curve here as my function, and the black sloped line is my chord between these 2 points at x coordinate of x and an x coordinate of x plus h. Okay, h being the horizontal distance between x and x plus h. So the theory of differentiation, as you know, is all about, well, what would happen in theory if this gap, this red point, came down the blue curve all the way as theoretically as possible, as close to the black point as it could, given that the chord line between them represents the average gradient of the curve around there, around that region. And so what we really want is, well, we don't want an average, we want an instantaneous gradient at x. So we need to close h. We need to make h as small as we possibly can. And the smallest value we can make h is 0, the distance between x and x plus h to be 0. Practically, we can't do that, we can't measure it. And at higher, it was sufficient enough just to tell you, look, if we close that gap and make h equal to 0, then we've got the instantaneous gradient. Now, what you didn't see was the actual maths behind the kind of proof, if you like. And that is what differentiation from first principles is. At higher, you were just told how to differentiate. This is going to have a wee look at the proof why. And there's a cool wee bit of mathematics in there that helps you do that. So this graph just highlights, how that happens. So we move the red chord, the red dot closer round the curve, make h smaller, and we'll get our instantaneous gradient. But let's look at the maths behind that. This is differentiation from first principles, this formula here. F dash of x equals the limit, this stands for the limit, right, as h tends to 0, right? And the formula, I won't get into how the formula came about, right? If you're interested, you can do a bit of research around that. But the formula is f of x plus h, take away f of x over h. And if you tidy that up and apply the limit function, you'll end up with the derivative. I usually quite enjoy demonstrating this. It's quite a neat piece of mathematics, this limit function. It's unlike anything you'll have ever seen before in the in your maths courses. And basically, what the limit function kind of says is, well, I want to theoretically make the value of h 0. I can't physically do it, but I want to mathematically investigate what would happen if h was 0. So we apply the limit function at the very end. Once we've worked out f of x plus h take away f of x over h, once we've worked this part out and apply the limit function, right, what would the function become if h became 0? We will end up with the derivative, right? I promise you. So we'll do it for a couple of common derivatives. So for instance, differentiate 4x squared. You know the derivative is 8x, right? You know that because at higher you were told multiply by the power, reduce the power by 1. So you were told that. Let's prove it using first principles. So let's do it in stages. Let's have f of x equal to 4x squared. Let's have f of x plus h equal to, now f of x plus h will be 4 times x plus h squared. Right, now we'll need to multiply that out, so that's 4x squared plus 2xh plus h squared. Tidy it up, 4x squared plus 8xh plus 4h squared. Okay, well, let's plug that all together, right, into the formula for differentiation from first principles. So it says the derivative is the limit as h tends to 0 of f of x plus h, which is this here. So 4x squared plus 8xh plus 4h squared. Oh, so we'll subtract that. Take away f of x, so take away 4x squared all over h and close that off. Now, before I apply the limit function, you have to get this in its most simplest form, right? So we have to get it in its simplest form. So f dash of x will still be the limit as h tends to 0. But look what happens, 4x squared to 4x squared is nothing. We're left with terms in h. So that'll be 8xh plus 4h squared over h. Close that off. And that algebraic fraction in itself simplifies. So we now get f dash of x equals the limit as h tends to 0 of, now if we divide both terms on the top here by h, we'll get 8x plus 4h. Right, now for the fun part, right? So you've done all this sort of boring algebra bit. Now for the fun part, apply the limit function. So we want to say, right, what on earth is going to happen as h tends to 0? So, theoretically speaking, if we could make h 0, what would happen to this function? Well, the only thing that would happen is that term would become nothing. Yeah, because if h became 0, 4 times nothing is nothing, and we would be left with 8x. So therefore, the derivative is 8x. But that works, doesn't it? That's what we expected. And actually, having done that process, you can see why this isn't taught at higher, and it's held on to until advanced higher. But it's quite a sort of neat process, and actually, as I say, if any of you are kind of budding mathematicians, or you're going into any sort of STEM sector, the limit function is an important one really to see in action. So let's move on. There's this example and another one that I want to do, just covering sort of different aspects, really, the algebra behind it. And then I've got 6 in a little worksheet for you to do. So let's have a look. Differentiate f of x equal to x cubed, add 2 from first principles. So we've got f of x is x cubed at 2. Let's work out f of x plus h. That's going to be x plus h cubed and 2. Right, well that has to be multiplied out. That's no use to us the way that is just now. So let's multiply this out. So what we're going to get, x at h times x at h squared, which we already know. Add 2. Keep multiplying it out. So multiply everything in the second bracket by x, just like it at 5. X cubed plus 2 x squared h plus x h squared plus. Now, you might come across scenarios quite a bit like this at Advanced Higher where you've got a lot of terms that look the same but the order is sort of swapped around. I like to kind of keep, when I'm doing this, I like to kind of keep a convention. So, like I've written these first two terms out with x's and h's in them, with the x's first. So I'm going to keep doing that, even although this multiplication that I'm about to do would suggest I should have hx squared. I'm going to keep myself right and go for x squared h. And as I say, the only reason I'm doing that is because, even at this level, you're on the risk of not spotting like terms you know, something you take for granted really at this level. So same in the next term, h times 2xh is 2xh squared plus h cubed plus 2. Right? And as I say, it was just about helping spotlight terms a wee bit better. So if when I'm doing things like this, just try and keep to a convention. X terms followed by h terms. So let's tidy it up. X cubed plus, so 2x squared h plus x squared h is 3x squared h. Xh squared plus 2xh squared is 3xh squared plus h cubed plus 2. And that's f of x plus h. So the algebra is a wee bit more involved there than it was with the last example. Let's apply, go ahead and apply the limit function now. So f dash of x is the limit as h tends to 0 of f of x plus h, which is all of this part here, x cubed plus 3x squared h plus 3xh squared plus h cubed plus 2, take away f of x, so take away x cubed at 2, all over h. Right, so starting to get a bit unmanageable now, isn't it? So let's have a little look, tidy it up. F dashed of x, limit h tends to 0 of, right, x cubed, take away x cubed is going to go. So now we've got 3x squared h plus 3xh squared plus h cubed 2, and this is going to be take away 2 is gone. That's all over h. Right. So cancel this algebraic fraction down. What have we got now? Dividing by h's, so f dash of x limit as h tends to 0 of 3x squared plus 3xh plus h squared. So that's it, as tidied up as it can be. Now apply the limit function. What would happen is h tends to 0. Well, as h tends to 0, that term goes to nothing, that term goes to nothing, and you're left with 3x squared. Right, now, does that marry up? Is that actually what the derivative of this is? Well, of course it is. So we've done it right. Okay, right, last one. Differentiate f of x equals 5 over x from first principles now. Let's just do this one first of all before we get started, so you can get a clear idea of what we're aiming for here. 5x to the power minus 1, so f dash of x is minus 5x to the power minus 2, or in other words, minus 5 over x squared. Right, job done. So that's what we're aiming for. Let's see if that is indeed what we get. So, differentiate, so we need f of x plus h. F of x plus h. Okay, easy enough. 5 over x plus h. So, what does this look like? Well, if you sort of give it some thought before we get there, you've got f of x plus h, which is an algebraic fraction. Take away f of x, which is another fraction. So we're going to have algebraic fractions to combine on that numerator there. So actually, before I go for this, what I am going to do is just work out what f of x plus h, take away f of x, is before I get to the stage where I'm dividing it by h. So f of x plus h is 5 over x plus h, take away 5 over x. Right. Combine the algebraic fractions. You can combine it in whatever way you like. I am still a big fan, and some of you will criticise me for it, I'm sure. I am still a big fan of smile and kiss, even at this level. Right, so what would we get? Well, we would get 5x, take away 5 lots of x plus h, all over x plus h. Right, perfect. Now, let's combine that now, see what we can get. So the numerator become 5x, take away 5x, take away 5h, all over x squared, add xh. Yeah, I might need to refactorize that later on. I'll need to see how we go on. Okay. 5x take away 5x is nothing, so now we've got negative, there's that negative sign we would have been looking for, negative 5h over x squared at xh. Happy days. Right, let's find the derivative. F dash of x, that is going to be f of x plus h minus f of x, so in other words, this. Oh, better write limit in, otherwise it's not strictly correct. Limit as h tends to 0 of minus 5h over x squared at xh all over h itself. Right? So really we kind of need to deal with this. So what I'm going to do is just come out here and deal with that. So it's minus 5h over x squared at xh times times 1 over h. Okay, that h cancels with that one, and we are left with negative 5 over x squared at xh. Right, so nearly there, last wee line of working. Let's come back to this. Alright, and the derivative is f dash of x is the limit as h tends to 0 of what we've got on the far right hand side here, negative 5 over x squared at xh. Right, now you might be wondering, surely at some stage, you're going to run the risk of getting a divide by 0. Well, you might, but largely speaking, if you've got that, you've probably done this wrong. or the derivative doesn't exist. Um, so, for instance, in this one, you might be thinking, well, hang on, I might get a divide by zero here, but you won't actually. As h tends to zero, it's only really this term that goes to zero. Yeah, the x squared term will go to zero. So actually, what we're going to be left with is negative 5 over x squared, which is exactly what we set out to get. Right? So that's quite a long process, that one. Right? It's quite a fair bit involved. But again, I think it's quite a cool process. And remember what I said, this is not examined at advanced higher, but it is widely accepted that you're exposed to it and you see it. So what I'd like you to do, there's a worksheet coming that's got six of these six functions to differentiate from first principles. Some of them are nice and easy like the first one. Some of them are a bit more involved and like higher powers beyond squaring, and some of them are fractions like this one that involve more. You know, if you're not that confident with the process and just manage the first two out of the six, it's not a big deal, so long as you've sort of tried. And for me, the important thing is the limit function. You know, if any of you are going to go on and study any sort of maths or engineering at this level, then really you need to have tried applying the limit function at some stage. Okay, so give those questions a go and give me a shout if you're stuck. Thanks very much.